A few weeks ago, I posted a video on the Diana lunar habitat. This video is based on a paper that looks at an alternative power solution for the base. Instead of relying on solar panels placed on the lunar surface, the ZEUS satellite constellation uses orbiting solar power satellites to beam energy directly to the habitat. This concept, detailed in a paper led by Dennis Acker in Acta Astronautica, offers an alternative solution for powering not only Diana, but also other lunar habitats, outposts, and energy-intensive activities like in-situ resource utilization and scientific experiments. Solar panels on the lunar surface generate electricity only when sunlight is available, which, even at the most illuminated sites, isn't constant. This requires backup power systems. Moreover, key scientific and resource extraction sites, such as permanently shadowed regions rich in lunar ice, often lie 20 kilometers or more from the base, complicating power delivery. The ZEUS system addresses these challenges by providing continuous beam power from orbit, ensuring a reliable energy supply even in the deepest and darkest craters. The ZEUS constellation consists of 300 solar-powered satellites orbiting the Moon. These satellites capture sunlight, convert it into microwave or laser energy, and transmit it to ground stations at the Diana base near the lunar South Pole. The stations then convert this energy into electricity to power habitats, rovers, and lunar regolith processing facilities. By coordinating the satellites' orbits, the system ensures at least one satellite is always in line of sight with the base, delivering uninterrupted power through lunar nights and varying polar lighting conditions. The Diana habitat requires 175 kilowatts, including a 20% margin above its baseline needs. As lunar activities expand, particularly energy-intensive tasks like mining and resource processing, power demands will grow. Space-based solar power is scalable by adding more satellites as the need increases, supporting long-term lunar exploration and development. The flexibility of delivering power using orbiting satellites supports all kinds of missions, from scientific research to industrial operations. Beamed solar power for lunar assets. While solar panels on the surface are the cheapest and most practical solutions for providing power to lunar habitats, rovers, and equipment, they do have some drawbacks. Many of the most interesting places to visit on the Moon are in permanent darkness and away from likely lunar bases. Even in sunlit areas, intermittent sunlight requires big and bulky backup systems. Nuclear fission reactors provide an alternative, but pose safety risks and require burial at a safe distance from inhabited areas. While nuclear power will likely play a role in lunar energy, beamed solar power from space offers a safer, more practical near-term solution. Space-based solar power, or SBSP for short, is in its infancy on Earth, but various startups are working on the technology, including Space Solar, which I covered on this channel last week. Unlike Earth-based SBSP, which is constrained by safety and atmospheric factors, lunar solar power satellites face fewer limitations. On Earth, microwave beams are capped at a power density of 230 watts per square meter, leading to low efficiency, typically 5 to 11%, and large, costly ground infrastructure is required. Lunar systems free from these restrictions can use high-power, high-density transmissions, achieving greater efficiency with smaller ground stations. This makes beamed solar power to the lunar surface an efficient and scalable solution for powering bases like Diana or the Artemis Base Camp and all the scientific and resource activities likely to be part of a lunar base. Location: Dergelash Crater. After evaluating multiple sites to the lunar north and south poles, the Diana team selected the rim of the Dergelash crater near the South Pole as the optimum location for the habitat. This site receives sunlight for 86% of the year, ensuring a reliable power supply, and lies close to permanently shadowed craters, likely containing water ice. The ice can support life support systems, provide drinking water, and enable propellant production. The relatively flat terrain simplifies construction, and nearby areas of high scientific value support research opportunities. However, these nearby regions receive sunlight only 30 to 60% of the time, complicating scientific studies and resource extraction due to the limited solar power availability. Commercial-scale lunar regolith processing demands substantial energy, estimated in the tens of gigawatts. Covering hundreds of square kilometers with solar panels to achieve this power level is impractical at the South Pole due to reduced solar visibility. Without gigawatt-scale power, significant resource extraction is unachievable. ZEUS mission plan and space solar alternative for lunar power. The ZEUS mission plan aims to deliver up to 1.6 megawatts of continuous power to the Diana lunar base, enabling scientific research, industrial-scale resource extraction, and support for a large crew. Its long-range, high-efficiency power-beaming satellites minimize energy loss, transmitting microwave energy to a ground station Rectenna located 7 kilometers from the base, with a radius of 4.37 kilometers. Shielded cables connect the Rectenna to the habitat, protecting against electromagnetic interference, or EMI, for the high power density microwave beams. Managing electromagnetic interference. High power density beams, likely using the 2.45 GHz band, common for wireless power transmission, pose EMI risks. This frequency is close to Wi-Fi's 2.4 GHz, potentially disrupting communication systems. Unshielded circuits could experience induced currents, leading to data corruption, signal noise, or component failure. Sensitive scientific instruments, such as spectrometers and radio telescopes, are particularly vulnerable if operating near the beam's frequency. Similarly, X-band communication devices at 8 to 12 GHz used for satellite links risk degrading signal quality. To mitigate EMI, critical equipment requires aluminium shielding, effective at micrometer thicknesses for microwave frequencies. Precise beam pointing, guided by a pilot signal from the Rectenna, ensures accurate energy delivery, reducing stray radiation and interference. The base and scientific instruments are already radiation hardened to withstand cosmic background radiation and solar flares, providing additional resilience against EMI. Space Solar's alternative approach. I won't go into the orbit selection or deployment of the satellites, the details can be found in the study. Instead, I will use the solar space technology to illustrate solar power beaming at the lunar surface, as the company is actively developing this technology and already has a contract with Reykjavik Energy in Iceland to deploy a 30 megawatt space-based solar power system by 2030. Solar Space's satellites are much larger than those envisioned by the ZEUS team. They consider the minimal viable product to be a 400-meter satellite that weighs 80 tons and can beam 30 megawatts of microwave energy. A single Starship vehicle can launch its components for in-space assembly by autonomous robots. After assembly in low Earth orbit, an orbital tug transfers the satellite to its lunar orbit. Alternatively, assembly could occur in lunar orbit, with the Starship refueled in low Earth orbit, delivering the pre-assembled satellite components to lunar orbit for final assembly. Space Solar's larger satellites contrast with ZEUS' smaller constellations of satellites, offering a different approach to achieving high-power delivery with fewer units. Orbit recommendation for space solar power satellites. To power lunar assets, particularly the Diana base near the South Pole, the ZEUS team evaluated various orbits, including frozen polar orbits, Lagrange points, and near-halo rectilinear orbits, ultimately favouring the NHRO. For this discussion, we adapt Space Solar's technology, which supports orbits like medium Earth orbit, high Earth orbit, geosynchronous orbit, and highly elliptical orbits to propose an optimal lunar orbit. The recommended orbit is a highly elliptical polar orbit. A highly elliptical polar orbit with its furthest point over the lunar South Pole maximizes power delivery to the Diana base. Its key features are extended dwell time, high eccentricity, for instance 0.9, ensures the satellites move slowly at its furthest point, lingering over the South Pole for extended periods as dictated by Kepler's laws. This maximizes power beaming opportunities to the base. Minimal shadow time. The high altitude at its furthest point reduces the likelihood of the satellite entering the Moon's shadow, ensuring near constant solar exposure, even for assets in deep craters like Shackleton, and polar coverage. The polar orbit provides regular passes over the South Pole, ideal for targeting the Diana base and nearby permanently shadowed regions. Power density and Rectenna size. Unlike Earth-based systems limited to 230 watts per square meter for safety, lunar satellites face no such restrictions. Power density of 1000 watts per square meter balances efficiency and electromagnetic interference risks. Rectenna area. For a 150 megawatt kite-class satellite, the required area is 150,000 square meters. For a circular ground station, their diameter is approximately 437 meters. This compact size simplifies lunar deployment while delivering substantial power. Constellation Design. A constellation of 2 to 3 kite-class satellites would provide sufficient power. Each kite-class satellite is 800 meters in diameter and can provide 150 megawatts of power output. The mass of a single satellite is 160 tons and can be assembled using 2 Starship vehicles. A total of 4 to 6 Starship launches provides between 300 and 450 megawatts of power to lunar assets positioned in the South Pole, including Shackleton crater and other permanently shadowed regions. Orbits would be staggered for continuous coverage and redundancy. Benefits. This orbit and constellation design powers lunar assets efficiently, including the Diana base and permanently shadowed regions like Shackleton crater. The high furthest point in the orbit ensures visibility into deep craters, while the compact Rectenna and high power density optimize infrastructure. Space Solar's proven technology, backed by contracts like Reykjavik Energy's 30 megawatt project, makes this a viable solution for lunar exploration. Upcoming events. Space Solar plans to deploy 150 megawatt power satellites by the mid-2030s, ideal for powering the Diana habitat and other lunar bases. To ensure continuous power, margin and redundancy, a constellation of multiple satellites is essential. Beamed solar power addresses key challenges for lunar operations. The most scientifically and commercially valuable sites, often in permanently shadowed regions, require reliable energy to support activities. Surface solar panels, while cost-effective and proven, only generate power when sunlight is available. Nuclear fission reactors could deliver substantial power, but are not yet commercially viable and pose safety risks. Despite its potential, beamed solar power has drawbacks. The technology remains under development, relies on affordable heavy lift vehicles like Starship, and introduces challenges such as electromagnetic interference. What are your thoughts on using solar power satellites to beam energy to lunar bases, rovers, scientific instruments, and mining operations? Share your ideas in the comments below. Thank you for watching. Space News Live is on Saturday evening or Sunday morning, depending where you watch from. I recap the videos I posted this week, answer questions, respond to comments and chat messages, cover any missed news, and preview upcoming content. I'd love for you to join if you can. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry, with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.